All right, recording is rolling. It is Wednesday, October 19th. So yesterday we did about half the textbooks I signed. So I want to go over the rest of this with you guys today. And I have some other demos of stuff lined up. I might push this off to tomorrow. I like to do an FRQ tomorrow. Got a ton of stuff. And then, well, we got 3 days this week to do this. All right, so there's a faculty meeting this morning. Just got back from that. This has to do with the laptops that are being checked out to students. So we're trying to get a laptop to every single student. So next Friday is going to be October 28th. We're going to have this bell schedule where you guys are going to be in first period for looks like 2.5 hours. Okay, and then you'll go to fifth period, which includes lunch, and you'll be in there. It looks like about an hour and a half, well, including lunch, right? Then you go to your sixth, and then back to first, right? And this whole day, right? So Friday next week is going to be dedicated to getting laptops checked out. Yeah, you guys have to watch like videos and do agreement, right? Right. There was a paper that you guys signed, had your parents sign, and you guys turned that in, right, for to take the laptops home. I think I had those from all you guys except like two of you. So got for almost everybody. What we were told at the faculty meeting this morning is that if you, but like if your parents don't want you to take the laptops home and back, or they don't have the, if the school doesn't have the agreement for them, that how this would work is that you go to your first period class, but then you're going to miss like the first 10 minutes because you'll be down in the media center, like checking one out. And then you would also miss the last 10 minutes of seventh period because you have to check it back into the media center. So you'd be missing like a ton of class time, which wouldn't be good to you. So they're really trying to get everybody to sign this agreement and really like take the laptops home so that you don't have to keep like checking them in and out and like losing class time. Okay. Anyway, so that's coming up about just over a week from now. Right. Where's this? All right, so yesterday we had just started this in the fire drill range, so let's get a look at this one. Okay. We got objects, okay, these masses, this many kilograms, this many kilograms, separated by this distance. Okay. And okay, what's the net gravitational force of an object placed exactly halfway between them, exactly midway, right? And then, then there's a second question, but let's just focus on that one first. Okay. Now, this one I want to handle a little bit differently than I normally do, because you guys know all these solutions are already posted online. But this one I just want to go ahead and walk you guys through the pre-written solution. Okay. So here's my two objects. Okay. They're separated by 0.4 meters. So if you place something exactly halfway between them, that'd be 0.2 and 0.2 meters, just like that. Okay. And the question is, what's the net gravity force on this object? Well, isn't this object being pulled to the left and also being pulled to the right? But more strongly, which way? To the right, right? Because this guy's more massive, and then for like equal distances, right? This reminds me of a concept that I haven't quite got to tell you guys, but some type of called Lagrangian points. Right? Actually, you know what, let's do that right now. Let's do one of these class demos. Right. I'll burn a few minutes, but that'll be right. Okay. Something fun to learn about. So let me share my screen too. Okay, there we go. So let's say between the sun and the earth, for example, do you think that there is a point where the sun pulls to the left as much as earth pulls to the right? Okay. And now, would that point be closer to the sun or closer to the earth? Yeah, closer to the earth, right? Because the sun is so massive that you need to be closer to the earth, right? And so that could be like a point of sort of gravitational stability. Now it's not super stable, kind of like trying to park a baseball on top of a roof, right? It's kind of like roll off one way or another, right? But gravity kind of washes out. You could probably do some small adjustments and keep the probe approximately there. Now, if you had like a static solar system, then that would be the only Lagrangian point, right? And of course, everything would just gravitationally attract and all pull together. Right? But because of orbital mechanics, there's also some other points that open up that are stable in a dynamic sense. For example, look at this point that says L2, right? If you were at, say, like a point like L2, do you think the Earth and the Sun would both be pulling you to the left? So there would definitely be a net force to the left. You'd be accelerating to the left. But what if you're like sort of in orbit along with the Earth, like you're along for the ride? Then that could be acting as a centripetal force, right? The Earth pulling and the Sun pulling, right? And okay, so then you can see that like the Earth beneath your feet, but you would never actually fall closer to it. You could just kind of like ride along in your own orbit, right? You guys see that? You guys remember space that Jim Webb Space Telescope that was sent up less than a year ago. It's been sending back really cool images of the universe. All right. That one has actually been set up in orbit about the L2 points. You guys see like a red looking orbit here, okay. Right? Because that's pretty stable. It's easy to just keep it in space in place there. Also, an advantage of having space probes parked at any of these points is that, of course, they're kind of out in space. They're like outside the atmosphere, right? So you can get better visuals. Okay. Well, if L2 exists, you can do a little bit of logic and say, well, by logical extension, there must be some L3, and I'll show you guys animation backup of L3 also existing. Right? Guys, what was the first year that a space probe was ever that people anywhere sent anything into space? 1957. Right, and that was what was that called? Sputnik. Yeah. Okay. Soviet Union set that up. Launched the space race. But before 1957, we had no idea what was at L3. There was a lot of speculation. There were good reasons why people thought that there was probably another planet here. I think they call it Vulcan, but we've looked. There's nothing there, but could have been, right? All right. So at some point in history, along comes a guy named Lagrange, does a bunch of fancy math, and says, "Hey, if you make equilateral triangles between, say you have two large masses like the sun and the Earth, you make an equilateral triangle, okay, that you'll get these two other points of stability. And actually, L4 and L5 are like the most stable. So like if you parked a space probe there and it started to like kind of drift out, it would sort of drift back into place, right? It's sort of like the opposite of L1. All right, so let's take a look at where is this? All right, so you're looking at the solar system from above here. Here's the sun in the middle. Here's Jupiter going around. Okay, here's the inner planets all flying around, right? Okay. So do you guys see those pink dots? What do you think those pink dots represent? The asteroid belt, right? The asteroid belt. Yeah. So those are all asteroids of the asteroid belt. See how that's kind of a triangular-ish looking shape? Okay? Because the two biggest masses in our solar system, well, by far the biggest one is the sun. It's like 99% the mass of the solar system. But the second biggest mass by far is like Jupiter. I think it's like more mass than the rest of the planets combined. Okay. So those two like drive the dynamics of the solar system. You can definitely see that here. Okay. See like Jupiter sort of protecting all these inner planets from a bunch of stuff that could otherwise be colliding with us, holding things in certain stability. You guys see like this corner of this pink triangle looking shape? Isn't that like the L3 point of the sun and Jupiter going around? Here's like the L3 point, right? And how about those two green patches? Those are also asteroids. Those are called the Greeks and the Trojans, just name people have given them, right? So, an old reference like the Iliad. So there you go. And those are at the L4 and L5 points between the sun and Jupiter. See like an equilateral triangle with the shape. All right, and that's where my computer freezes, but that is all right. Because done with that demo. Let's okay, switch back here. All right. So I want to show you guys that at some point. So there you go. All right, so this is not that. That just reminded me of that. But we're parking something like geometrically in the middle. Right. So there's a force to the left, there's a force to the right. We're saying what's the net force? Well, the net force would just be well, since it's left and right, you can take the difference, right? There's opposite directions. Right. Okay. So you can quantify the magnitude of each force by G(m)(m) over r squared, where G is universal gravity constant. Right. Capital M could be, well, one of these masses. So let's go like the 500 and the 200. So this could be capital M for one of them. This could be capital M for the other. Right. The lowercase m might refer to this 50 kilogram guy in the middle. Right. And then r could refer to the center to center distance, which happens to be the same for both of them because we've placed it geometrically in the middle. So that's just going to be 0.2 meters. You guys get that? Okay. So you can run this equation, just pop the numbers and pop. Okay. It's a good exercise to be able to do this right from scratch. Like somebody just threw this problem. Of course, you guys know also that AP probably wouldn't give you anything exactly like this. You have to have the skill. Like it's a pretty fundamental skill, just be able to set up an equation and pop in numbers. Right? Okay. So it ends up being the difference between this and this, which ends up being comes up to like this number. Okay. And if you want to like throw in prefixes, micro is like 10 to the minus 6. So if you have 2.5 times 10 minus 5 newtons, call it 25 micronewtons. It's a basic thing. Okay. There was a part B to this question. That's just part A right there, right? Okay. Part B was like, well, where could you place this object so that the gravity fields like did cancel out, so there was zero gravity, which actually does link back to like those Lagrange points. So it's sort of like the L1 point. You can think of it that way, sort of like the L1 point between these two, right, where all the gravity cancels out. Okay. And for this, I've got real small here. Let me zoom in where you guys can see this. Okay. Well, we're like sort of like solving for x. So we've got x, and if the total distance between two is like 0.4 meters, would the other distance be 0.4 minus x? We've got x and 0.4 minus x. Okay. Now we don't know what x is. Right? Solving for x, like the unknown. Okay. So you can set a very similar type equation. Right. Now, the way I set this up is I said the force to the left would have to be equal to the magnitude of the force to the right. Right. Or you say one minus the other is zero. Right. And then it would just lead to the step anyway. Okay. And then you can solve for x. And it looks like it's probably going to be quadratic, except it looks like from here to here, I was able to bypass quadratic formula because you can like square root both sides, right? That's right. But I mean, algebraically, there's different ways you can solve this. I'm sure you could pull out a quadratic formula, different method, different path through the forest, right? Okay. All right, so do some math, and you can actually solve for x, which of course it'd be closer to the smaller mass, right? Closer to the 200 kilograms than the 500 kilograms. But you would have predicted that before you ever started. Okay. Okay. Right. So again, this has been uploaded to Google Classroom for a few weeks now. You guys have this. Okay. I think that's a pretty good way to do that one, just to walk through it. Okay. Guess that. All right. Let's move on here. All right, we've got 43 and 47, which are actually really similar type problems. So we'll do 43, and then so you guys would say instead of having it with 47. We've got a satellite of Mars called Phoebus. So when they say a satellite of Mars, they're talking about like an actual satellite, like a moon, right? The fancy word for moon has an orbital radius of this many meters. Right, so they're telling you from the center of Mars to this moon, right, that distance, and its orbital period is. Look, they very conveniently gave it to you in seconds, which is you would never just in natural conversation pull out a number like this, right? You might say, oh, it takes so many like Earth days for the moon to go around or something like that. But they gave it to you in seconds, which you would have to convert it to seconds anyway, because that's the base that's for time. Okay? Assuming the orbit is circular, which again, you guys know it's actually elliptical, but it's probably pretty close to circular, right? So determine the mass of Mars. Right, so like, how do scientists know what the masses of all these planets are? You can go to Wikipedia and just type in like, what is the mass of Mars, and get the answer to that question, right? But how would they know this? And they would know this by doing this exact math that we're about to do right here. Right, so 43. Right. Get you guys a picture. Imagine you guys are seeing this anyway, but we've got Mars. I'll call it, could be like capital M, but larger mass. Right? We got a moon over here. This, right? And there's it's like orbiting around, right? Going around. There's a center to center distance from Mars to this moon. Maybe I'll call that. I have to call it capital R, like a fixed distance. Okay. Here's capital M, here's lowercase m. Okay. Okay. All right. Let me set this up from scratch, just like AP would expect you to do if this was an FRQ question. What they would want you to say is that there is a gravitational force between these two, and that's acting as the centripetal force holding this moon in orbit about the planet Mars. So the setup would go like this. The centripetal force is provided by the gravitational force, right? And if I draw that force, of course, it's if they want a free body diagram, they say force, equal and opposite forces. Okay, well. Okay. And centripetal force is, of course, mv squared over r, and gravitational force is gm over r squared. Okay. Any questions so far? What any of these characters mean, where they come from, why the setup? Yeah, go ahead.
Why is it centripetal force then?
Okay, so because it's an orbit, right? So whenever there's a centripetal force, like something, if there's something moving on a curved path, like going around a curve, right, there is some kind of centripetal force involved, and you can calculate with mv squared over r. But remember, centripetal force is never just a lone force by itself. It's always provided by one of the classic forces. And a recent lab you guys did, it was provided by the tension in a string, which of course is also equal to the weight of the hanging bucket. For a turntable situation, like what force are holding these Roosevelts on here? Well, there'd be a friction force, right? Okay, would be providing the centripetal force. Okay, or in this setup, the gravitational force would be providing the centrifugal force. Right? Sometimes there's multiple forces and they conspire together. Like you guys had a recent FRQ or sorry, AP classroom question where there's like a ball on a vertical string, right? And it had both weight and tension. And depending on where the ball was, you could either add those two together or take the difference, right? It goes at the top or the bottom of the vertical circle, right? And the net force was providing the centrifugal force. So in this case, there's only one force on this planet,
It's just like that.
gravitational force. There you go. Okay, so you guys got that? Okay, so we got this set up. Now, in the past, what we've done is solve for this V velocity, right? We're not going to do it here, but this has taken a turn before where you can say V equals the square root of GM over R, which is, I think one of these posters up here says orbital speed is that. Now that's not where we're going with the story today. We're going with the story today. Instead of solving for this V, we want to solve for the mass of the planet Mars. Right? Hey, do you guys see something that cancels out? Maybe the mass of the moon? Right? Right. Well, whatever the mass of the moon is, doesn't matter. As long as it's pretty small compared to the planet. Right? And that is consistent with orbital velocity being, or orbital speed being independent of the mass of the satellite too, right? That goes away. One of these, okay, that reduces. Okay. And if you do a little algebra switcheroo, you're going to get mass of the planet Mars is the orbital speed squared times the radius divided by the universal gravity constant. Wouldn't that be true? Right. Okay. That's it. Now, suppose the only measuring tools we have are like a telescope and maybe a clock or a stopwatch of some kind, right? So we're watching this planet go around through the telescope, and you could probably say, okay, watch it go around and around and around. Probably get a pretty good indication of what this R is going to be. So we could sort of get that by observation, pop that in. Okay. We have experimentally verified calculations for G, so we know what G is, just a universal constant. Okay. How about this V? Hey, would this orbital speed be something we could calculate this pretty much the same way you guys calculated this speed, right? In this lab, right? Something to do with like the circumference divided by the time period, right? And they told you the time period, and circumference is just 2 pi r, isn't it? Right? So maybe I'll do substitution for this V. I'll say, okay, so we got the mass of the planet Mars, capital M. Here, I'll put a subscript Mars just to make it, in case you're looking through your notes, like, what is capital M? Mass of Mars, right? So in the place of V, I'm going to go circumference equals 2 pi r, right? And then it does that in some amount of time period t, right? That's what the V is, right? Okay. And then this r is still here. This universal gravity constant is still here, right? Is that true? Second. Right. Now, okay, see, 2 r's there, another r here. I got fractions and fractions. I can clean this up a little bit. And I think it's going to go like this. Mass of Mars is, okay, we got the 2 pi being squared. I got r, so that's like 3 r's multiplied together. Okay. I got a universal gravity constant g down here, and I have a t squared. Okay. So there you go. There's, in terms of variables, an expression that could give you mass of the. So yeah, if you guys break out a telescope, if you have a pretty good telescope, you can even see like moons orbiting Jupiter. Okay. You can do the same thing for Jupiter. Actually, that's the next question. Okay. So we have a general expression to get the mass of any planet just watching the moon go around it. Okay. Right. So now we got that expression. Okay. You guys good so far? Okay. You know what? Let me just go ahead and flash the solutions up here because the rest is just plugging numbers in, right? Which you guys can do. Right. So like this. Okay. So there's the expression. Okay. Plug some numbers in. Okay. And you get the mass of Mars in kilograms. And then here's an even better picture of what this could look like. Okay. You guys good? Of course, one trick too is make sure you can plug these numbers to the correct scientific notation into the calculator. And I'll go ahead and do that really fast. Okay. So if you guys are like writing anything down. Okay. So go open parenthesis 2 pi close parenthesis square that multiplied by, okay, the radial distance was 9.4 times 10 to the 6 meters. 10 to the 6 is a million, right? So 9.4 million meters. Close that to the power of 3, so keep it. Okay. Then divide by. I've got a bunch of stuff in the denominator, so see, like if I had one parenthesis, if I did divide by and open up only one parenthesis, as soon as I close the parenthesis, it stops dividing. Okay, so it's just like how do you operate a calculator, right? So I'm gonna open up a ridiculous number of parentheses, just to make sure I'm always dividing everything else. We got 6.67 times 10 to the negative 11. Such, it's universal gravity constant. And then 28,000 seconds. Right, very conveniently, they told you the number of seconds it takes for the planet to go around 28,000 seconds. Okay, and that's being squared. Okay, so there you go. There's the mass of Mars. Remember, Earth is like 10 to the 24 kilograms. Oh, so Mars 10 to 23 kilograms. Okay, Mars is a little more than a tenth of the mass of Earth. Next question. 47. Oh, one of the moons of Jupiter, named is that Io? I think it's like Greek pronunciation Io. Okay. It goes Latin, I think it'd be Io, but let's go Io. Has orbital radius of this many meters and a period of this many days, which is probably a more colloquial way to say that, right? Like Earth days. Imagine the orbit is circular, probably pretty close to true. Calculate the mass of Jupiter. Right. And then there's a follow-up question where we're looking at a different moon with a different set of numbers, right? And then they say, hey, well, compare that. Okay. So isn't it just going to be like the same setup, except it should be Jupiter, right? The only extra step you have to throw in here is to exactly converting days to seconds. Let me see. Converting days to seconds, right? Okay. Okay, so we're back to the same general expression, right? As we derived before, right? Just a mass of a planet, blah 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 blah. Blah. Okay, just plug stuff in. Okay, so right, days to seconds. You guys can convert days to seconds. Look, I got some railroad track dimensional analysis. Okay, maybe that could have been a separate step. But you could calculate the number of seconds. So you want all your times to be in seconds, right? Can that be true? Okay, you guys can follow this, right? So part A was one of the moons. Part B was just they picked a different moon. But I mean, this is almost identical to the Martian problem, right? Otherwise, okay. So I think it's better to just do it this way. Okay. Right. And then one of the moons came out to this many kilograms. The other moon came out to this many kilograms. Okay. So to 2 sig figs, it's like definitely the same number. Now, if you go to the 4 sig figs, it's supposed to rely on that many significant figures. Think, okay, looks slightly different. Okay. Okay. Guys, okay. Maybe because the orbits are slightly elliptical. Maybe because actually this whole Newtonian gravity is really just an approximation of what later Einstein came up with, that general relativity. So if you have like crazy big masses, Newtonian mechanics kind of breaks down it for like 2 large masses and like 2 extreme conditions. Okay? All you need are Newtonian mechanics to like launch the Apollo program and get to the moon and back. But yeah, if you want to do some a little bit fancier physics or get crazy precision or run a GPS system, you actually need like Einstein physics, which is a bit more precise, more accurate than Newtonian. Okay. All right, that's it. All right, now this next question I really like a lot, and this is closer to like an AP thought process, because what we've done so far, a little bit of derivation, like you should definitely have that derivation skill that you guys have seen the last few problems. Okay, but then at some point you just like plug and chug, and okay, so hopefully you should definitely be able to do that. Okay, but this problem I really like a lot. Right? Show that the escape speed from the surface of a planet of uniform density is directly proportional to the radius of the planet. Okay. Now, truth be told, see that escape speed right there? Really, you need conservation of energy to derive that, which we haven't done yet. Different textbooks do chapters in a little bit different orders, but we can still do this. Like same principle hold. Okay. And actually, I want to go off on a bit of a tangent, take you guys on a little adventure. We're going to loop back around to this problem. Okay. So, you know what? I'm going to show you guys Paul Hewitt, because about that. You haven't seen Paul Hewitt in a while. All right, share screen 2. Bam.
Any object in the center would have no gravity.
Whoops. He just gave away something I was going to ask you guys. Okay, so suppose you got a planet. Here, let's go on this adventure. Let's tunnel down to the center of the planet. Now, we're going to ignore the fact that it's all molten and blah, blah, blah. We're just focused on like gravitational mechanics, right? So suppose you like tunnel down to the center of a planet. There's like a cave right in the middle, that cave in the center of a planet. Okay. What would you feel like right in the middle? Would you be floating around like an astronaut, or would you feel extremely heavy? How do you guys think you'd be floating around like an astronaut, right in the middle, floating around like an astronaut? Aha, winner, yeah, right. Yeah, I just got floating around like an astronaut, right? Because isn't there like a sort of a gravitational attraction between you and every single grain of sand on the earth, right? And wouldn't that all cancel out in the middle? That you got this way, this way, this way, this way, this way, right? It's all pulling different ways. So the net effect is zero. You'd be floating around like an astronaut. Another way to think of it, suppose you took a bathroom scale with you and you're like, I'm going to stand on the scale. At the surface, you'd stand on the scale, obviously. But in the center, like, where would the floor even be to like stand on the scale? Well, there wouldn't be, right? There'd be like, there. So yes, you'd be floating around. Now, back to the top, back to the surface. All of us have spent our entire lives at the surface of a planet. Right? You guys know that like the Earth pulls you straight down. You can basically treat the entire mass of the Earth as if it's a single point right at the center, and the math works out pretty close. Right? But if you wanted to break it down, you could say, well, if you broke the Earth into like a trillion parts or like a bajillion parts, it's like there's gravitational force between you and every single grain of sand, but all the right stuff and all the left stuff cancels out, and so the net effect is just down. Right, but here, there you go. Okay, so right at the center, you would have like zero weight, right? But hey, what if there's like what about the journey down to the center? What if you have like a spiral staircase? So we dug ourselves a spiral staircase all the way down to the center of the planet, right? What would your weight be like as you go down? Well, at the surface, you have whatever weight you have, right? At the center, it's zero. I wonder what is the relationship? Like if you're halfway to the center, like right here is halfway to the center. I wonder if you would have exactly half your weight at the surface, compared to the surface, or more than half or less than half. Okay. And that's closely related to the textbook question. So, what is this? Okay, now I think we're good. Okay, so hold on to that idea. But part of the explanation actually involves what he's about to explain in this particular video, which is, let's say we're exploring the galaxy and we come across this really weird planet. We don't know it's weird at first, but we get around, we start exploring out. We're like, hey, gravity field doesn't seem as much as it should be for a planet this size, like this volume. And then we start to tunnel into it and we realize right away, oh boy, we have an eggshell planet. Do you guys see a giant eggshell planet? Right? You're like, hey, I know what we should do. Let's jump inside it, because that seems like a logical thing to do. What's going to happen inside this eggshell planet? Something really weird.
Because it'd be pulled in all directions equally. Do we see that? But what I want to do is I want to convince you that it would cancel out no matter where you are. And so what we'll do is we'll take a point that's about here, where this distance here is twice this distance. Do you think it would still cancel out this side and this side? What we'll do is we'll consider a solid cone of material. We'll call this M1. We'll call that D1. We'll call this M2 and 2D. Well, just D and 2D. Let's look at our equation. Let's have the equation guide our thinking, guys. The force over here would be our mass, say the mass of the point, okay, times M1 divided by D squared. That's this force. The force that's pulling over here, you might think it's more because it's more mass. Or you might think it's weaker because it's further away. And guess what one does to the other? See, when you're out here, it'd be twice as much this way, but twice as much this way. So how big would M2 be compared to M1? Do you see it's 4? It's 4. So M2 would be 4 times M1. That'd be like 4 M1s, boom, times your mass, MP, divided by this distance here, 2D squared. But when I take the twice the distance and I square it, what do I get, gang? Isn't it like 4D squared? And what do the 4's do? And what's this? The same darn thing I got here. So you know what? The pull here, equal. I just took a place that was easy because I got twice the distance here as here. You put any distance you want and that will happen. Anywhere inside there, there'll be no gravity. There'll be no field region. Inside a shell like that, there'd be gravity-free region. There'd be no gravitational field due to this mass. It would cancel out everywhere.
Yeah, so inside an eggshell planet, the gravity would cancel out. Now, hold on to the idea because that's about to be relevant. Okay, now I'm not going to go to this question exactly, but I'm going to solve a different question that's pretty similar. Okay, so let's go on that adventure into the center of the Earth down that spiral staircase. Okay, So, so now we're back to just a regular solid planet. Okay, so regular solid planet. Okay, got our shovel and a lot of time on our hands. We're gonna shoot, tunnel all the way down to the center. Okay. That cave in the center, we know would be like floating around like an astronaut in the center. Okay. Okay. I wonder, like what about like here? So taking a scale along with me, I'm standing on the scales and like going down the spiral staircase. All right. What's my weight like halfway to the center, something like that. So halfway to the center, would it be true that here, like this elevation basically, okay, that all the elevation above you is like a bunch of concentric rings, bunch of concentric shells, all just put together, right? And every single shell is going to cancel out, just like he showed you, right? Just did a quick proof of that. So this one, the gravity cancels out. This one cancels out. This one cancels out, right? Don't they all cancel out? So all the dirt above you in elevation effectively cancels out, right? And the only mass that ends up pulling on you is just like this region down here, right? It would just be like a smaller sphere. You guys imagine it'd be like a smaller sphere, right? Right. So your weight, now your weight is type of force, okay? G-M over, well, they do a lowercase r, so this could be variable, right? So over r squared. R is your distance to the center, like this, okay? Right, so G-M over r squared, okay, where capital M is the mass of the Earth, which I'm treating as if it's a single point right at the center. Okay. Your mass is little m. Okay. But remember, if you're like halfway down, okay, everything above you in elevation is canceling out. Okay. So this capital M is sort of variable. You can think of it that way. So your weight, yeah, I'm trying to see what's the weight of this guy standing on the scale. Okay. It's equal to, got universal gravity constant. Okay. I'm gonna substitute and place that down. Hold on to that idea, because your mass is obviously your mass regardless. Right? And this r, now this r could be a variable. That's why I made it lowercase. I'll do a special r could be capital R. That's the original phrase of the planet, but lowercase r could be like up to this place for example. All right, so go ahead and put that there. Okay. Now I need like the mass of just this right here. Now mass of a sphere could be like 4/3 pi r cubed. Right, you guys know that 4/3 pi r cubed. So we got the volume, or sorry, the volume is 4/3 pi r cubed. Right. And isn't mass density times volume? Mass equals density times volume. Okay. That's Greek letter rho represents density in this case, right? So suppose it's like common density all the way through. It's like the same dirt and stuff, right? Right. So if I take this volume and multiply by the density of the material, that could tell me the mass of whatever's beneath you in elevation. Isn't that true? Right? And that could be for any r. Okay. Now, do you guys see that? Even if you didn't know that volume of a sphere was 4/3 pi r cubed, right? Even if you didn't know that, all you would have to know to get the rest of this correct, right? The relationship that I'm trying to get you guys to see is that volume is proportional to the cube of. All you have to know is volume is proportional to r cubed. Okay. Now the volume of the sphere, more exactly, is 4/3 pi r cubed. That's where this bit comes from. Okay. But you see how some of the r is going to cancel. Okay. So the gravity force on you as you're walking down the staircase is equal to the universal constant, universal gravity constant. We got the density of the dirt. We got a 4/3 pi. We got your own mass, right? And then r cubed over r squared, isn't that all multiplied by r? Right? R cubed over r squared just reduces to r. That just became r to the 1. Is that true? Okay. And you guys see that all this fun string stuff is just going to be constant. That's a universal constant. That we're assuming constant. That's just a number constant. Pi is a constant, and your mass isn't changing, so that's a constant too. So this is just a string of constants, right? And so do you guys see that your weight would just very simply be directly proportional to how far you are from the center? Right? You guys see that? Right. Okay. Now I want to put this in a graph and add to the story a little bit more. Okay. Let's do a graph version of this. Okay. So now you guys see there's a direct relationship between how far you are from the center and what your scale rating would be if you're standing on scale. Let's go. What is your weight in newtons as a function of where you're standing in meters from the center? Okay. So here would be the center of the Earth. There's a very special distance, which is the surface of the Earth, right? And then, okay. Now all of us have spent all our entire lives at the surface of the planet, okay? Just at the surface. So we know that. We know that at the surface, your weight is just, you should just call it mg, right? Mass times gravity field at the surface. Okay. This is all our entire life's experience. This is all we know, right? This is all our brains really, like, okay, yeah, I get that, right? Sure. Okay. Now remember, at the center, you'd be floating around like an astronaut because every grain of sand pulls you in a different direction, so it cancels out. So, right. And then what connects these 2 points? Well, that's what I was just showing here, right? It's just like y equals mx. You guys see y equals mx, right? You guys see that? Right. So how am I going to connect those 2 dots? Yeah, a line, just a straight line. That's a direct relationship. Right? That's what I just spent the whole last paper showing. Right? That's a straight line. Okay. And the slope of this line is this crazy stuff. Right? G rho 4/3 pi m. Okay. Again, even if you didn't know the volume of the sphere exactly, what's important is that you know that volume is like some r cubed. It's proportional r cubed. Okay. Okay. Here's that. Now, how about this? Let's add to the story a little bit more. Let's say you take off in a rocket. Take off in a rocket. Okay. Now, as you get further and further away from Earth, okay, now this formula takes over where the relationship between the gravity force from Earth pulling you back and your distance from the Earth, because this little r could extend outside the Earth, right? It's just some general r. Now we've got an inverse square relationship. Okay? Inverse square relationship. So as you get further from the Earth pulls on you less and less and less. If you get crazy far away from the Earth, that force approaches 0, doesn't it? Right? So can you guys complete this graph? Like here's the surface of the Earth. Now we're going to take off in a rocket. We're going to go beyond the surface of Earth. What does the rest of that graph look like? Give you guys a head start. See if you guys can draw it before I draw it. Okay. Let me throw 1 point on the board. I think you guys probably have it by now. Let me throw 1 point on the board. Suppose you double your distance from the Earth, like to 2r. This hash mark would be 2r, right? R, 2r. Right? Right. So another way to say that is, suppose you had a ladder that was 1 Earth radius tall, in which the top of that ladder. Okay. Guys, what would your weight be if you double your distance from the center of the Earth? You guys are saying 1 over 4, right? Because if a factor of 2 squared, see, like if you stand on top of a ladder that's 1 Earth radius tall, you've effectively doubled your distance from the center of the Earth, right? If you throw a factor of 2 on that r, it's also becoming squared, so it'd be like 1/4 of your weight, right? So here's 1/4 of your surface weight. Wouldn't that be like a point like right there? That picture? Now it's just a single point on this graph, but more generally, 1 over r squared. Like if you graph y equals 1 over x squared, doesn't it? It's like a curvy looking graph, right? With a horizontal asymptote down here. In that picture. Okay. So if you get crazy far away, it approaches 0 newtons. Right? That's true. Okay. So the most you can ever weigh in the vicinity of any planet is right at the surface. Right? If you tunnel down, your weight goes down. Okay? If you take off on a rocket, again, the gravity force goes down. Okay. You guys good so far? All right, now let's go actually address the question they asked you, because remember how if you tunnel down into the Earth, the gravity force on you is proportional to your distance from the Earth? Okay. Well, it looks like they're hinting towards a very similar outcome for escape speed. Show that the escape speed from the surface of a planet of uniform density is directly proportional to the radius of the planet. Now, when we get to conservation of energy, I can derive this for you guys, but you guys see the answer. That there's a poster up there that says orbital speed ends up being square root g/m on r, which I've derived for you guys before. Okay. But escape speed, here's what it ends up being. I'll prove this to you guys someday. Okay. Square root 2g/m on r, okay, which by the way is the square root of 2 times the orbital speed. Right. So orbital speed of See if you want to stay in orbit around the Earth, in low Earth orbit, say International Space Station. How fast is the International Space Station going? It's about 8,000 meters per second. So if you take 8,000 meters per second, multiply by the square root of 2, I mean, that's the relationship from here to here, right? Okay. That would be the speed that you would need. Now, as long as you're directed straight away from the Earth, right? That's about 11,000. It's a little over 11,000 meters per second, right? 11,000 meters per second. So suppose you're going like 12,000 meters per second. So you're going just straight away from the Earth. You could cut off your engines, and you would have enough inertia, like enough momentum at that point, to fly away from the Earth forever, even though they were tugging on you back. But no, you just fly away forever. Okay? So escape speed, right? Now, supposedly, this is also proportional to the radius of the planet. So you can just glance at the sides of the planet, and if you assume it's the same density, same material, same dirt, whatever, blah, blah, right? Supposedly, if the planet has like twice the radial size, it would also have twice the necessary escape speed. Right? That's what the book problem is saying. That's the context. And they say, prove that. We can prove that. Very similar to what we just did like last page. Because that m, the mass of the planet, is proportional to r cubed, isn't it? Right? So the fact that mass is proportional to r cubed. Right? Now, if you want to get more exact, you say mass is density times volume, and the volume is 4/3 pi r cubed if it's a perfect sphere, which is pretty close. Right? Not exactly, pretty close, right? Okay. Yeah, maybe I can just substitute that whole expression in there. Why not? So escape speed is equal to the square root of 2 times universal gravity constant times the mass of the planet, which is density times volume, 4/3 pi r cubed for a sphere, all divided by radial size of the planet. Okay. Move r a little bit over to the right side just to set up that cancellation, right? Like that. Guys, r cubed divided by r, that's r squared, right? Okay. And it's all inside a square root. What's the square root of r squared? R, just r, right? So escape speed in general is, we got square root of, well, 2 times 4/3, I get 8/3, right? Got an 8/3. I got the universal gravity constant. We got the density of the material that makes the planet. We got a pi thrown in here, right? And then in the square root, all multiplied by, and again, the square root of r squared is just plain r. So escape speed, therefore, is directly proportional to the radius of the planet. Okay? And all that square root stuff is just constant. Okay. Yeah. Oh, okay. Yeah, go ahead. Okay, you guys good there? Good? All right. Okay, we've got 4 minutes. That's perfect for this last one right here, number 75, the last one. A popular amusement park ride, got a rotating cylinder. They told you the radial size of this thing, and they said that it's angular speed. Angular speed, that's how fast it's rotating, right? Radians per second. Oh, they gave us radians per second. Ooh, that's good, because it said revolutions per minute. We'd have to convert it to radians per second anyway. So they gave us a very convenient unit. Okay. The floor drops away and the passenger is suspended. Now, guys, if there was no friction, wouldn't you just like slide down? It doesn't matter how fast. If there's no friction, you're just going to slide down. Okay? So the only force that's keeping this person in place is friction. Okay? And the question is, what's the minimum coefficient of friction between the rider's clothing and the wall to keep the rider from slipping? Remember that the magnitude, okay, so static friction is coefficient of friction times the normal force. Okay, just remember that. Okay, so you know what? Since I only got like 2 minutes here, I'm just gonna flash a pretty written solution for you guys and just walk you guys through this. Okay, so here would be the free body diagram. Okay, this guy has a weight that's trying to pull him down. Okay, now the friction force. Notice this is not normal force going up. This is friction force, isn't it? And that's what's keeping him in place, like checking his weight so he doesn't like slide off. Okay, the normal force is actually horizontal, wouldn't it be? Right. This is a weird looking free body diagram, right? Because usually the normal force is opposite of the weight, but not in this case. Do you guys see what that would be? And do you guys see that the normal force would be acting as the centripetal force, right? Which has something to do with how fast it's spinning. So here, if you know the mass of the person, right, and you know, actually that's going to end up canceling out at the end anyway, but let's just throw an m as a variable. Okay, you know how fast it's rotating, that's omega, radians per second. Okay, square that times the radial size of the cylinder, right? That could represent the normal force. Okay, so that's there. We got the weight there. Okay, And we would ideally like the friction force to balance out the weight, right? And friction force is coefficient of friction times normal force. So we can feed all these expressions into, well, we said that in equals, right, in the equation. So I want the friction force to be equal to coefficient of friction times normal force, which is also equal to the weight. Okay. Normal force is this expression, substitute that in. Okay. Do a little algebra, you can solve for the coefficient of friction, which is here. You guys see that the math cancels out. Right, so it doesn't matter if we're talking about like little kid or big adult, the math cancels out. Okay. So you should definitely have this. You should be able to do this from scratch, right? This could be a really good FRQ. Like you go take the AP exam in May, and they could totally give you this problem, and you have to be able to definitely get up to this point to solve in terms of variables. Okay, can you guys have that skill? Right, I know I find this problem to you guys, so take this as an opportunity to sit down at home with a blank piece of paper and see if you can do this like from scratch without looking at the solution. Right, definitely to here, because once you get to that point, you can just like pop in the numbers, right? You guys can do that. Okay. And then you get coefficient of friction. Okay. No, this is the minimum static coefficient of static friction. So if you have like coefficient of static friction of like 0.2, you're good to go. If it's 0.1, oh boy, this is going to slide off and die. Okay. Good hits. Okay. And with the last 20 seconds here, I just want to mention that the last question that's printed here, number 76, I do like this question a lot, but it does involve conservation of energy, which again, we haven't hit yet because different orders of things. So this question might come up in the future because I like it. But anyway, who's got any questions? Any questions? All right, I think we're doing pretty good, pretty good. All right, so I will see you guys tomorrow. Enjoy the rest of your Winter's Wednesday.